Hello everyone, my name is Sudhanshu Rasal and today I am going to introduce you to our project on design and development of the compressor assisted ejector refrigeration system. The group members working on this project are Sudhanshu Rasal, myself, Ruturaj Furande, Prajwal Narke and Abhishek Jagtap. We are the final year mechanical engineering students of JSPM's Jaywantrao Sawant College of Engineering, Pune. The project is carried out under the guidance of Dr. P. A. Patil. Relevance and significance. We know that VCRS, vapor compression refrigeration system, are used in day-to-day life appliances to huge commercial refrigerator and huge industries like automobiles. VCRS has many advantages but comes along with few disadvantages also. To eliminate this disadvantage, we come up with an idea of compressor assisted ejector refrigeration system. The disadvantage of VCRS is it becomes inefficient at higher condensing temperature. This higher condensing temperature may result due to higher compression of refrigerant or higher heat absorption in the evaporator to achieve more refrigeration effect. In order to achieve higher refrigeration effect, one has to bear the loss of energy consumption due to the compressor work. In compressor assisted ejector refrigeration system, condenser temperature has inverse effect as that on the simple vapor compression system. As an increase in condensing temperature, compressor assisted refrigeration system works more efficiently without compromising energy consumption. Instead, work required for the compressor is reduced to some extent in compressor assisted ejector refrigeration system and reduce the energy consumption, hereby also increases in compressor life. Objectives. The four main objectives of these projects are thermodynamic analysis of the compressor assisted ejector refrigeration system, design and development of the system, investigate performance parameter by comparison of this compressor assessment ejector refrigeration system with a regular vapor compression refrigeration system, validation of theoretical results with experimental results. Left hand figure shows the schematic diagram of ejector refrigeration system along with the pH chart on the right side. The four main components of the systems are compressor, condenser, ejector and evaporator. Ejector has two inlet, primary inlet and secondary inlet shown by the point 3 and 9 respectively. Most of the refrigerant coming out of the ejector goes back to the compressor and rest to the condenser and then evaporated through the expansion valve. On the right hand side, the pH diagram shows the different isentropic and isenthalpic processes carried out in the various components of the system. Thermodynamic analysis of compressor assisted ejector refrigeration system. While doing thermodynamic analysis, we use the refrigerant HFC134A. Various processes carried out in the different component of the system are explained here. Process 1 to 2 is the compressor work, and to calculate the compressor work the formula used is explained here. Process 2 to 3 expansion work in the ejector. Process 3 to 4 is a mixing of primary and secondary refrigerant flow. Point 4 is the mixing point of the refrigerant coming out of the compressor and the same refrigerant coming out of the evaporator. To calculate the enthalpy at point 4, energy balance equation is shown here. Process 4 to 5 is the process of isentropic increase of the pressure in the ejector. Process 5 to 6 is the condensation in the condenser. Process 6 to 7 is the process of expansion work, and the process 7 to 8 is the by far the most important process where we get refrigeration or the cooling effect. To calculate the cooling effect, formula used is shown here. Enthalpy at point 8 minus enthalpy at point 7. To calculate the COP, the conventional formula is used. The ratio of refrigeration effect to the compressor work multiplied by the entrenchment ratio. Condition used and the result. While doing the thermodynamic analysis, four conditions are used, and these are the compression saturation pressure, that is the primary pressure line at 75 degrees centigrade. Similarly, condensation pressure line at 55 degrees centigrade, evaporator pressure line at 10 degrees centigrade, and ejector pressure line at 5 degrees centigrade. The enthalpies obtained during the thermodynamic analysis at various points are shown here. Entrenchment ratio mu is equal to 0.41. Entrainment ratio is the basically ratio of secondary refrigerant flow rate to the primary refrigerant flow rate. The COP is calculated as entrainment ratio multiplied by the ratio of refrigeration effect to the compressor work, and after the calculation the COP is coming out to be 7.503. The thermodynamic analysis of simple vapor compression system. The similar conditions are carried out in the in the analysis of simple vapor compression system, and the various points located and the enthalpies of this point are calculated from the pH chart. The COP of this simple refrigeration compression system on the same operating condition as that of compressor assisted refrigeration system is calculated, and the COP of this system is coming out to be 6.07142. This is the model prototype of the setup we are currently working on. The various components like compressor, condenser and ejector and evaporator are shown on the setup. Comparison of coefficient of performance of both the systems are carried out here. The graph is plotted between the COP of the systems against the condenser temperature. From the graph, it is shown that COP of ejector refrigeration system is more after certain temperature of condenser, while the simple vapor compression refrigeration system become more inefficient with that temperature. Conclusion: the thermodynamic analysis of system shows 23.57% increase in the COP of the system than the conventional vapor compression system after a certain temperature range of condenser. As in increase of condenser temperature, performance of the simple vapor compression system decreases exponentially, whereas the performance of ejector refrigeration system increases exponentially.